All right, so let's go for today's class. Hopefully this will work. All right, so again, this is ES 305. This is our second lecture. And today is January 18, 2018. Okay, so we're going to continue with the first chapter. All right? So in the first chapter, now what can we do? We can look at some concepts that are really important. Okay? So let's say here, let us consider a power cycle. All right. So over here, generally the sketches you will have is that, let's say, this box over here is your power cycle. Okay, think about your steam engine. All right? So what is the goal of having an engine? To be able to get out of it work or energy, no? But basically will be work. So what we want to get out of this is work that you can use to whatever you want. Move a piston or do any activity. So in order to create work, what do you do? Let's say the steam engine, what do? You need to apply heat. So basically, you will have here what is called a hot container, but they like to call those things a hot reservoir. Generally, I don't put reservoir, but this is the first time. So this is your hot reservoir. And this hot reservoir is going to be providing heat into your system. Okay? So, am I missing anything in this sketch? What am I missing? You're going to lose something. Okay, so that's a good thinking. But if you think about it this way, really, if you look at it this way, there's nothing wrong with it. No, you can say, okay, if I have an ideal system, I should be able to transform all the heat that I put into the system into work, no? Or vice versa. If I put work into the system, I should be able to produce an equal amount of heat. Okay? And this is really what we'll be doing next. This, if you leave this sketch as it is really what we call the first principle of thermodynamics. Is that the equation will tell you that yes, it is possible to transform all the heat into work, or it is possible to get the amount of heat that you put providing a similar amount of work. Okay? But is that what really happens in real life? No. In real life, what happens is that you're going to have losses. But those losses will come from what? They will come that every single engine, you put heat, but it's also working at what? At a certain environment, correct, but it's working in a certain environment, no? So this one they call reservoir. So basically, let's say this will be Q cold, okay? Just to keep the color notation. So we kind of discussed that a little bit the first day when I was trying to give an introduction about the class. Is that I ask you, when is your engine more efficient? Your one of your car. In cold weather or hot weather? Cold. Why? Because the temperature difference between the hot reservoir and the cold reservoir, the higher it is, the more work you can provide. Yeah? The closer the temperatures are, the less work you can provide. All right? That's why, I mean, what do they say about computers? Don't you need to keep your computers cold? All right? The reason is because of this, no? If the temperature is close to the environment, it's not, I mean, if it overheats, it's not good, okay? But if it's cooler, it's going to be faster than if it's warm. I mean, I never checked, but maybe you can check once if your phone, let's say you do, or your computer works better today outside or when it's really hot in the summer, no? Okay, but all right. So this is really what's happening. So if we did not have this one, what should be the efficiency? 100%. But because everything operates between two different temperature reservoirs, we will have an efficiency. Okay? So there is three different type of, if you want, cycles we can study. The main one is the power cycle. So what will be the efficiency for this cycle? So before we go to the efficiency, what is a general definition of the efficiency? In general, you don't even need to tell me for this case. What is efficiency? Okay, so in general will be whatever you get out divided by whatever you put in, no? Yeah? So if you want, let's write that to make it simple. So what you get out divided by what you put in. Okay, so the efficiency of the power cycles, they have different ones on the textbook, but I think they use the letter eta, this letter over here. So what are you getting out of this system? Work. We can put here work. And what are you putting in? And what do you put in? I mean, just look at the figure. What are you putting inside the system? Heat, no? So it will be the Q hot. All right? Then, what do we say about the work? The work is proportional to what, or is equal to what? You're going to get more work if you have a bigger difference between these two reservoirs, no? So really the amount of work you can get is equal to what? Q hot minus Q cold divided by Q hot. All right, so if we simplify this, what are you going to get? 1 minus QC over QH. Okay, so later, this is very easy to understand, but it takes about 4 or 5 pages to prove it, but later in the class, we will prove that this equation here, that the efficiency, which is equal to 1 minus Q cold over Q hot, is equal to what? 1 minus, so if you have a cold reservoir, this will be at a certain temperature, Tc, no? if you have a hot reservoir, this reservoir will be at a certain temperature, T hot. So we can say that the efficiency will be equal to what? 1 minus T cold divided by T hot. But actually, this equation involves 4 or 5 pages of derivation. Okay? And also, this is an equal sign here. This is true just in an ideal case, okay? Otherwise, you need to leave it this way. But slowly, okay? So here, what's important, this is, I think, one of the most important concepts from this class, is this one, is that every engine is working between two different temperatures reservoirs, no? So whatever power you can get, or what you can get, is going to depend on the difference of the temperature between those two reservoirs. Okay? For example, if you want to remove heat, a lot of heat from your car, it's going to be easier if the water is cold, no? That's why you have a fan that is trying to remove the heat as fast as possible, no? Yeah? From the water. All right? Okay? So, oops. I want to break the page. Already broke it, so. All right. Just a little bit. It's not a big deal. Okay, so let's see, page. So page 9. So not today because it's cold, but most of the year we are happy that we have what in Florida? Heat, but when we're inside, refrigeration, no? Got refrigeration. So this time let's say this is your refrigeration cycle. So again, we're gonna have, I'm just gonna put hot this time, a hot reservoir. And we're gonna have a cold reservoir. Okay? So if you understand the figures, you don't need to know to memorize the equations. You can derive them very quick. So in order to, let's say, cool down a room, okay? What do you need to do? You need to, okay. Do you need, but basically to refrigerate something, what is it to put cold or to remove heat? Okay, it's true that the way it's done most of the time is called remove heat, but that would be the next thing, would be called a heat pump, no? Removing heat. But if you try to cool something, what are you trying to do? Put cold into a system, no? Yeah? So it would be your Q cold. So now if we go in this direction, that means what? That if you look at it from this way, you will be removing heat, no? This would be your Q hot. And in order for this to happen, is this going to create work or is going to require work? It's going to require work. So this time you need to put work inside. Okay, so what would be the efficiency of the refrigeration cycle? So they use the letter beta, generally for refrigeration cycles. So again, what was the general definition? Is whatever you try to get out divided by whatever you need to put in, no? Okay? So let me start by the denominator. What do you need to put in? Work, no? Why are you trying to get out of the system? What are you trying to achieve? To put cold, so that will be Q cold. Alright? So if we do the same thing as before, this will be equal to Q cold divided by what? Q hot minus Q cold. Or this will be equal to Q cold, Q hot minus Q cold. Or same thing we derive later on. We're not going to derive this one, but you could derive that this should be equal to T cold over T hot minus T cold. Okay, where beta here is the refrigeration efficiency. Okay, any questions so far? All right. So let's see if the last one you can almost do it on your own. So page 10. The other type of system you can analyze is, instead of the refrigeration, is what is called a heat pump cycle. And this time you do the same thing, the same figure. So this will be your heat pump cycle, which needs to operate between a hot temperature reservoir and a cold temperature reservoir. Okay. And this is work. So now what do you think you need to achieve on the heat pump? You said before. It's going to remove heat. So you're going to remove heat from the system. So it will be Q hot is coming out. And then what's going to happen to the cold over here? It needs to go in, no? Okay. Will this create work or will it require work? Require work to put into the system. So for the efficiency, they use the letter gamma for the heat pump. You can change them, okay? It's not a big deal. Okay, what are we trying to get out? Remember, efficiency is whatever you try to get out divided by whatever you put in, no? So what are we trying to achieve over here? Remove heat, so QH, no? In order to achieve that, what do we put into the system? Work. So this is equal to what? Q hot divided by Q hot minus Q cold, or if we follow the same as before, gamma will be equal to Q hot minus Q cold, or this will be equal to T hot minus T cold. Where gamma will be the heat pump efficiency. Okay, any questions so far? All right, so let's try to do a problem. There's always one that I do. Let's see what it is. Hopefully it's on the 8th edition. Let's see, page 11. Let's say here, example, and let's see if I can find the example somewhere over here. So instead of going to Canvas and extract the PDF file, I know I have it somewhere over here. What is this? I think it's in here. I think it's in here. Okay, so you got here those efficiencies. You see, it just give it to you in this way. Power cycle, the refrigeration cycle. Oh, call it coefficient of performance. Call it efficiency. Okay. I will go faster, so I'll do this. Oops. Oh, okay, good. I came here. We need to do this stuff then. Afterwards. Oh, I think it's this one. I think it's the one. This is the one I do all the time. Okay, so let's look at problem 286. Okay, so just copy what you have over there. So basically, I'm just going to do the figure. All right. Do this figure over here. Those two figures side by side. So it's a figure 286 shows two power cycles A and B. So doing circles. So A and B, which are in series. So basically, one is getting hot temperature from a reservoir Q1 and is removing heat at a reservoir temperature Q2, and this will be okay. So this is here Q2, and this one is removing heat to a third reservoir. Here will be Q3. All right. So each one of these two power cycles creates work A, work B. So that's the first figure on the left-hand side. The second one, I think, means if you have A plus B. So they say operating in series with the energy transfer by heat into cycle B equal in magnitude to the energy transfer by heat from cycle 2. All energy transfers are positive into the direction of the arrows. Determine an expression for the thermal efficiency of the overall cycle consisting of cycles A plus B operating between Q1 and Q3. Okay. So I don't have to press over there. That would be my mistake. So I think I need to come here. Okay, so what do we need to do? I forgot to read the most important part. Determine an expression for the thermal efficiency of the overall cycle, this one, consisting of cycles A and B together in terms of their individual thermal efficiencies. Okay. No, I need to switch to this one. There we go. So what would be the overall thermal efficiency? So what would be the efficiency for this cycle? Let's say what would be the efficiency for A plus B? By definition, it will be equal to what? What are we getting out of this one? Work. It will be omega sub A plus omega sub B, no? What are we putting in? Q1. Okay. So basically what they're telling us that we need to find an expression for the efficiency of this full cycle in function of the efficiency of this one over here. So this one will have an efficiency eta sub A, and this one will have some efficiency eta sub B, no? Yeah? Okay, so let's see. This is a bit of algebra, but that's all I see over here. So this is, we need to rewrite this expression in order to find the efficiency A plus B just in function of the efficiency of A and the efficiency of B. So what is the best thing we can do? What is the efficiency of A? So it will be work A was trying to get out divided by Q1. Okay? All right, maybe let me add one thing here to this one. I don't know if we're going to need it or not, but I'm trying to put as many questions as we can over here and then decide. What will be the work A equal to? So it will be equal to what? Q1 minus Q2, no? And the work of B will be equal to what? Q2 minus Q3 divided by Q1. Okay, so maybe I should have left some space, but it's going to be a little bit crowded, but if you want, let me just put it here. So basically, at the end, we have the efficiency of A plus B will be equal to what? What we have over there, Q1 minus Q3, no? Divided by Q1, which is what we're expecting. Yep? Yeah, so this is crowded over there. So let's say this would be this one here. This is the one. So now, this one over here, what is omega sub A? We just did it, but that will be equal to what? What would be omega sub A? Q1 minus Q2 divided by Q1. So this will give you that, I don't know why I want to keep writing in that direction, that omega sub A will be equal to, is it better if I do it that way or not? I don't know. 1 minus, we'll find out, okay? 1 minus Q2 over Q1. All right? I see how to solve this problem. Okay. Okay, guys, that's why I write down the equation. It gives me time to think about how to solve the problem. So I have this equation, this equation. Now we could do the same thing for the efficiency of this power cycle, no? So what will be for the power cycle B, what will you have? Work B divided by Q sub 2. And work of B will be equal to what? Q2 minus Q3 divided by Q sub 2. So this will give you that the efficiency of B will be equal to 1 minus Q3 over Q2. All right, so I think the way to solve this problem will be to do what? What is the variable that we want to try to remove? What are the variables we have over here? Q1, Q2, no? Q1 and Q3, sorry. All right? So what can we do? We can maybe rewrite Q1 here in function of this efficiency and Q2, no? Yeah? And then we can do the same thing probably with Q3. We can write Q3 in function of Q2 and see what happens. I hope those Q2 will cancel, okay? Hopefully. If not, we'll have to find about a different way. So let's say this will be equation star. This will be equation 1 in Roman and 2 in Roman. Okay, so page 12. So let's see. Let's say from equations 1 and 2. Let's see, what can we get? So the first one will be efficiency of A equal 1 minus Q2 over Q1. So I mean, let me do the algebra. So this will give you what? -1, so it would be 1 minus the efficiency of A. I'm multiplying by -1 on both sides, will be equal to what? Q2 over Q1, no? What am I trying to do? I'm trying to rewrite Q1 in function of Q2. Okay? So this will give us what? Q1 equals to Q2 divided of 1 minus the efficiency of A. If I do something similar with the other one, this will be equal to 1 minus Q3 over Q2. So this will give you 1 minus the efficiency of B equals to Q3 over Q2. And this time we can to rewrite the expression of which one? Q1, Q2, or Q3? Q3. So Q3 will be equal to Q2, 1 minus eta sub B. Okay, so now what can we do? I think we can go and substitute into this equation. So let's see if that would work. So substituting into the star equation, which is what? Q1 minus Q3 divided by Q1. So what do we get if we do that? So this should be equal to Q2. I don't know how to present this one. Okay, let's do this one. Q2 over 1 minus eta sub A minus Q3, that will be Q2 1 minus sub B and all this is divided by Q2, no? Yeah, so I can just put here Q1, sorry. I can just put here, this will be 1 divided by Q sub 2 divided by 1 minus the efficiency of A. Correct me if you see something wrong, okay? Okay, so do I need to factor out the Q2 to see that it's going to cancel out? Probably not, no? I hope you see that this Q2 will cancel with this one, no? Okay? So here we're going to end up with one expression that will be equal to what? So let me so I'm moving this one to the top. Did you see what I did? I just moved this one to the top, no? Okay, that's all I did. So now, this will give you what? If I multiply this one by this one, what do you get? 1 minus 1 minus sub A times 1 minus sub B. Do you think if I click here, it's going to finish everything, or it's just going to... No, let's try. No, good. It's just going to minimize it. Okay, good. So, all right, couple more lines of algebra to simplify this expression over here. So if we come here, oops, okay. So if I do that, what do I get? Will be equal to what? 1 minus, if I multiply this one, will be 1 minus 1 minus mu sub B or plus, because it's minus minus, no? Let's just do it this way. So 1 minus 1 minus mu sub B minus mu sub A plus mu sub A mu sub B. So at the end, this one cancels out. So we get that efficiency is equal to what? Efficiency of A plus efficiency of the circular power cycle minus the product of both of them. Okay, so let's see if we can give some meaning to this problem. So generally the efficiency of a car is how much? What is the efficiency generally of a combustion engine? 30%, so that's 0.3, no? So let's say we have, this one is 0.3, and let's say the other one is a similar engine of 0.3. Okay, so basically if we do this, then what will be the efficiency of A plus B? Will be 0.3 plus 0.3 minus 0.3 times 0.3. So what do you get? So 0.6 minus 0.09, so 0.51, no? Yeah? All right, so is that possible? Can we get a combustion engine with a efficiency of 0.51? We just said that the top you get is generally about 30%, no? Okay, so what is the utility of this problem, let's say? Let's say you do the design of a system. And you say the required power for that system is whatever, a certain amount omega sub A plus omega sub B, no? Okay? In this case, with those temperature changes, Q1, Q3, will you be able to generate that amount of power? I mean, you could if you had an engine whose efficiency was 0.51, no, 51%. However, what is the efficiency of an engine generally? It's 30%. So if you had Q1 and Q3 fixed, what would be the only option for you to be able to provide that amount of power? To put two engines in series, no? Okay? So these all type of problems you can solve this way. So depending on the application, what is more efficient? To put maybe two engines in series or maybe to put two engines in parallel? No? We could put A and B in parallel. No? We can put the same temperature Q1, A and B, and see what would happen. Okay? So depending on the applications, one might be more efficient than the other one. I mean, might be more suitable than the other one. So sometimes if you say, for example, oh, my design needs that much power, it's your role to find something that can provide that much power. All right? Either you're going to have one huge engine, no? Or you might have to have two smaller engines in order to provide the same amount of power, no? Okay? I mean, it's like during the hurricane, those power generators, no? You have ones that can power the basic utilities, but what happens if you want to power your air conditioning with a generator? Can you use the same one? Generally, the ones you buy at Lowe's and those things, I mean, the lower ends cannot power your refrigeration unit, okay? You need to go to a much higher power. So sometimes you want to be smart, just buy one for the refrigeration, for the AC, no? And one for the rest. Okay? Otherwise, you need a very big engine if you want to be able to do both things with one. Okay? All right, so this is what we did. 1, 12, 13. We still have time. Okay, so since the book is open, let's see if they have problems about that. 286. So let's see, 287. It's provided. Okay, so let me give you some problems here. Run them down. So let's see, homework 1. I might add some problems, but for now, let's say problems 287. I like the ones with figures because it gives me an idea what the problem is about. So 290. So this will be some type of power cycle and refrigeration same time. This is a refrigeration cycle. Let's see that one for a heat pump. 292, so 92. And air conditioning, let's say 293, okay? Heat pump, a heat pump, yeah, so 293. So for now, you have that. Chapter 2, we say problems so far 87, 90, 92, and 93. Okay? for now. What did I do? I have no idea how those things can happen. Okay. Okay. Okay, so by looking at this problem, what is the other thing that we need to do in this chapter that we haven't really covered, looks like? Is the heat transfer modes, no? Like, remember we said that in this class we don't really care about how you transfer the heat, we care about just the amount. But I told you that we still give you a little introduction about how the heat can be transferred. So basically you can transfer the heat under which form? You can transfer it through conduction, convection, or radiation, okay? So even though this is a whole class just to study, actually this is a whole class just to study conduction and convection. I think there should be a completely different class for radiation, okay? But again, so we give you like a little introduction. So let's go to this camera here. So I will add problems. Maybe let me just go to another page. So page 14 will be heat transfer modes. Okay, so we said that we have three main heat transfer modes that were one, conduction, two, convection, and three, radiation. Okay, so I like to give, it's not 100% exact, but I like to give, like keywords for you to remember, which are important. Okay, so what is something very specific to conduction? You need a solid medium. Perfect. Solid medium. So basically the heat, if it wants to go through this wall, it needs to go through the medium solid wall, no? Yeah? Okay? Now what is something specific to convection? You need some type of flow, no? Flow medium, or yeah, flow medium. I like more flow than liquid, so flow medium. For example, the fan doesn't really cool the room, but it helps you to remove the heat faster because it's moving the flow in the medium, no? In the class, if you want. All right? Okay? What is specific about the third one, radiation?
No medium.
No medium. Perfect. Okay, so let's start. Now I'm going to give you the basic equation. So let's start by the first one. Let's say 1 here. Conduction. Okay, so the typical example of conduction. So remember, every time there is an equation, it should be some type of figure or sketch, no? The equation does not show up magically. It's like in statics, you do free body diagrams, you write down equations. All right, get used to that process. So let's say we have a wall over here. So generally no, always heat goes from what? Hot to cold or from cold to hot? Hot to cold. It's like you go from high pressure to low pressure, no? All right. So let's say if this room is hot and the outside is cold, if you open the door, what's going to happen? Is the hot going to go out or is the cold going to come in? If there is no wind, okay? So let's say you are today by your house. You heat the inside of the house, but there is no wind. If you open the door, what are you going to say? There is cold coming in, or should you say there is hot coming out? What is really happening? There is hot going out. Okay? So when you say close the door, there is cold coming in. No. There is hot coming out. Okay? If there is no wind, obviously, okay? Was the perfect conditions. Alright? So anyway. So we go from hot to cold. So let's say in this side is hot. So let's say we have a temperature here T hot. The wall inside will be outside will be at temperature T hot, or inside, I mean, it's not a good day for today, but generally outside is hot, no? In Florida. And inside will be what? Cold. Okay? And we know that we want the heat will be going from hot to cold. And I put a little dot on top because really, when you talk about heat transfer, is in function of time. Okay? So this is really what is happening. All right? So the equation that gives you the conduction, all right, should be equivalent to what? If you look at the figure, it should be in function of what? TH, T cold, no? So it should be equal to the difference in temperature between those two, no? Okay? Maybe I forgot to put something here. And what should be this? This is the thickness of the wall, no? So if we needed to give an equation for this line, what would be the equation of this line? This is one line. Lines have an equation, no? I mean, the general form would be what? dt dx. Yeah? What would be dt dx really? Would it be T hot minus T cold divided by x, no? What would be the angle, correct? Okay, I don't have space to write all that stuff. So, basically, the heat should be proportional to dt dx. And now, with the heat, the way the heat is being going out, will it depend on the what material the wall is made of, or it will be independent of that? For example, if you have a wall made out of brick, will the heat go through the same way that if your wall was made out of wood? So basically, the heat transfer depends on the material, no? Okay. So let's say the material property here is K, okay? Then, will the heat also depend? If you just look at a surface this big, or if you look at a surface this big, it will be bigger, no? The more surface you have, the more you have. So it should be, so basically the equation, I give it to you, is minus Ka dt dx. Okay, we just say now that if the heat goes from hot to cold, that should be the normal direction, so that should be the positive sign. Okay? So can anyone tell me why did I have to put a minus in front of it? The reason is just mathematical. we say how to call this positive, no? Okay, what is that line or the dt dx? What is the slope of that line? Is it positive or negative? Negative. So really, this should be equal to what? Minus ka dt dx should be equal to what? How do you find the slope? Final minus initial, no? Yeah? Over x. That will be your dt dx, correct? Right? So this term, you agree that this term is negative because th is higher than t cold, no? Okay? So personally, every time I need to solve a problem, even though I know this is equal to minus ka dt dx, what I like to say is that this is equal to ka, and what I do is that I follow the direction of the flow. I go from what? From T hot to what? T cold along a wall thickness of x, no? So if you write it this form, you don't have to put the minus sign, correct? Because now this is positive, no? Here you have negative, negative becomes positive, no? So negative, negative becomes positive. However, if I just put this one here, I can just leave it that way. So where k over here, let's say k is the material conduction coefficient, A is the exposed area, X, if you want, is the wall thickness, and dt dx is what is generally known as the temperature gradient. Okay, so in order not to start a new page, I'm just going to put it over here, but we say that K depends on the material. So if you have a material that is a good insulator, do you think K is going to be a high value or low value? Low value. If you have something that is good conducting heat, what should be the K? High or low? High. So generally, if you think about it, materials that are good at transferring heat are the ones that are also good, that can transfer also good electricity, no? That are good electricity conductors. All right? So we look at this, I don't know by memory, but so let's go over here. So thermal conductivity constants or values. Wait, table. Show you, I'm going to load faster this way. There we go, let's open this one. So for example, if you have metals, no, that's not good. Okay, so let's see. Let's think about, okay, aluminum. Aluminum, is it a good electrical conductor? So it's about 205, no? Okay, so let's say aluminum. We put over here. Or which one you want to use? Copper, maybe? Maybe copper is going to be better. So let's see. Copper is a better electrical conductor. Concrete.
This is all thermal, right?
Yeah, but it should be, they should be related. Did you see it here? Did I miss it? Oh, okay. Copper, so what is the one for the copper? K for copper. So you can write down K copper. Is what? The 401. May I do a little bit more next time? Then, so this is a conductor. What should be a good insulator? I mean, there are these ones like air. Is air a good insulator, really? Yes. Air is a good insulator, no? But the other one they use sometimes is the, I'm sure they have an insulator system here. Glass a good one, but let's look at small values. Let's see, 0.15 clay, dry moss, cellulose, nitrate, acetate. Let's look for small values. Cotton wool is 0.029. Cotton is 0.04. Cork is a good insulator, no? So I don't know. I just want to put one, okay? So let's say cork, okay? Oh, I'm sure there's another one. Feathers. All right, let's do fiberglass, okay? Whatever. Okay, fiberglass. I'm just writing here. Is of the order of 0.04. So that's what I did put on the notes. I just wrote those two values over here. So in order to conclude, can you stop the heat transfer? Can you stop the heat going through the wall? No, but what can you do? You can slow it down. So if you slow it down enough time, it might be dark, and now the process is going to go the other way, no? But it's not something you can stop. It's something that you can slow down, and that's why you put insulation. Okay? It's like really the fan does not cool the room. It's actually heating the room, no? But by increasing the convection, it's making you feel cooler because you remove the heat faster from your body. But it's not cooling anything. It's actually heating, no? Okay? All right, so we stop over here. Guys, I'm not going to put a due date on the homework because I need to add problems, but you can start working on those 3-4 problems that I gave you if you want. Have a good weekend.